back. I hope this is the last snow video we have to do for this year. But looking at some derivatives, other derivatives, we're getting really close to the end of the derivatives section. As far as new derivatives are concerned, we're going to look at derivatives of inverse functions. We're going to look at derivatives of using the chain rule. But today we're going to look at derivatives with the exponential functions. And I typically go through a long proof of this, but because we are crunched on time, I'm just going to explain it very quickly. For y equals e to the x, if you graph the graph of y equals e to the x, the graph goes like this. Now notice how this graph is always increasing. Going from left to right, it's always increasing. It increases at a slow rate here, and then it increases at a particularly steeper rate as the farther we go to the right. So what winds up happening with this graph is that whatever the y-coordinate is at every point is also what the slope is at that point. So the derivative of this function in itself is e to the x power. So that's going to be a difficult one to memorize, I know. Now we go to the natural log of x. Well, we get to the derivative of the natural log of x, and again, there's a way to show this exponentially, but for right now, we are just going to take it that y prime equals 1 over x. So these are our two different functions. The other one is y equals a to the x. Now, you might start off by thinking, okay, well, if it's a to the x, then the power rule says bring this to the front and then subtract 1 from it. But that's when your base is the variable. Here, our base is a constant. The derivative of this is a to the x times the natural log of a. Now, so if I have that y equals 2 to the x, the derivative would be 2 to the x times the natural log of 2. And you may be wondering, well, why would e be different from any other constant? Again, e is a constant. It's an irrational constant, but it is a constant. Well, what happens here is if you do use this definition here, you got e to the x times the natural log of e. But the natural log of e is 1, so it's really e to the x times 1, which is simply e to the x. So these are three of the functions that we're going to look at. The derivative of e to the x is itself e to the x. The derivative of the natural log of x is 1 over x. And the derivative of a constant to the x power, or just what's basically an exponential function, is a to the x times the natural log of a. All right, now let's go a step further with this, and let's look at how we can apply this, and we'll look at some applying it with the product rule and so forth. So let's say that we have that y equals e to the x times the sine of x. Okay, well again, we've got a product rule here. So y prime is going to be the first term, e to the x, times the derivative of the second term. And again, the derivative of cosine is cosine. And then plus the derivative of the first, well, guess what that is? It's e to the x, and then times the second function, which is sine of x. Now, if at this point right here you wanted to factor out an e to the x from both parts, there may be situations where you could factor out an e to the x and it would cancel out somewhere later on. But for right now, we can just leave it like that. All right, let's look at another one. And I'm trying to, the more practice we get, the better. So let's look at y equals to the natural log of x times the tangent of x. Okay, well here y prime is going to equal to, okay, the first term, natural log of x, times the derivative of the second term. So what is the derivative of tangent of x? Well, if you have to look back through your notes, that's fine. But it ends up being that it is secant squared x. So now plus, all right, Now it's the derivative of the first term, which would be 1 over x times tangent of x. So it's the first term times the derivative of the second term plus the derivative of the first term times the second term. So that's another example here. All right. Let's go with y equals x squared times secant. Or let's do a quotient rule problem. X squared over tangent of x plus 1. All right? Well, okay, so we've got the derivative, again, using the quotient rule. Whoa, got to working too fast. So it's going to be low, which is the tangent of x plus 1, d high, 2x, minus x squared high, d low, okay, the derivative of tangent of x is, again, secant squared of x, plus 1, the derivative of 1 is, of course, 0, so there's nothing else out there, all over the tangent of x plus 1 quantity squared. Now, when we get to this, if we have a binomial in the denominator, we're not going to actually square it. We could make it tangent squared x plus 2 tangent x plus 1, but we're going to run into situations, we start getting into the chain rule where this term's going to cancel out. So we want to leave this alone. All right, well, at this point right here, just a little bit of cleaning up we can do. Doesn't really matter. You could actually leave it like this if you wanted to, but there is an x in common with both terms, so I'll pull out an x. And then I'll be left with 2 times the tangent of x plus 2 minus, all right, we factored out one of those x's, so it's just going to be x times the secant squared of x, and then it's all over the tangent of x plus 1 squared. So those are 3 good examples. I'll be looking forward to seeing you again Tuesday, and we can get some good bit of practice in and keep up the good work. Bye.